Let's take a listen as Brandon talks about these clouds and perspective.
Of these clouds. These clouds
Yes.
are going down at an angle towards the ground. Yes or no?
Actually, it'd be more accurate to say that the clouds appear to converge to the horizon. Now, flat earthers always like to use streetlights as an example, and we should be able to agree that the actual size of these streetlights does not change. It is the angular size that changes with distance. And since perspective is based on the actual size and distance of an object, we can use a scale orthographic drawing to understand exactly why we see the perspective that we do. In this case, I have streetlights that are 25 feet high, 20 feet apart, observer with a 5-foot eye level, and of course these lines represent the light hitting the observer's eyes from the top and bottom of those streetlights. And it is this convergence towards eye level that makes these streetlights appear smaller in the distance.
So this is how I would represent them if I were to, let's say, get a piece of wood and try to build this in my living room. I would angle that top board
What?
at the sky down at the ground, right?
Why would
And
you
then
draw
I'd
it
draw
like
the
that?
clouds on there, and it would look something like this.
Well, the problem when you draw it this way is that you have distorted reality because perspective does not change the physical world. The height and distance of these three clouds has changed. The ground has physically risen up to the eye level, and it only appears to rise up to eye level. That is a huge difference. And also, the vanishing point is much too close to the observer.
To use you can use a flat earth perspective and use straight line, use trigonometry, and you never have to change the elevation or the altitude of the clouds, and you're gonna have smaller angles as distance increases.
You're going to have
Correct.
smaller angles, but you won't have the angles that will match reality.
So what is the visual angle? The visual angle is the angle a viewed object subtends at the eye, usually stated in degrees of arc. It is also called an object's angular size. And over here, there is a trigonometric formula to calculate that angular size. Now, when objects are far away, you can simplify that calculation by using this trigonometric formula right here. It will give you the same answer. And since perspective or the visual angle is based on the actual size and distance of the object, I can use that formula to calculate the angle of the street light above the observer's eye level. So in the first street light, we have a distance of 20 feet, a height of 20 feet, 45-degree angle. At 40 feet, 26.6 degrees. At 60 feet, 18.4 degrees. And at 80 feet, 14 degrees. I can do the same for this 1,000-foot building at 2,000, 4,000, 6,000, and 8,000 feet in distance. Now the subject is going to move to this photograph, and I think everybody is familiar with this picture. Now, to be honest, I am really not certain who is representing the globe, but what he's going to do is he's going to analyze this picture using both globe curvature calculations and flat earth trigonometry calculations.
And what you'll see is that with the earth curve calculator, the hidden of the mountain should be about 1,365 feet, which is about half the mountain, which is circled as being hidden confirmed. Now we go to the flat earth part of it on the bottom with trigonometry. The angle to the top of the tower from the observer should be about half a degree. The angle from the observer to the top of the mountain should be about 0.56 degrees, meaning from the observer, the mountain should be higher in angle than the tower, but we don't see that in the picture, doesn't conform to flat earth.
Because you're applying trigonometry, right?
Correct. He is using trigonometry because on a flat earth, elevations are based on mean sea level of flat water. So here we have the distance from the observer to a mountain. The elevation forms a 90-degree right triangle, and therefore the visual angle can be calculated with this formula right here. And in the case of this photograph, these calculations show that the mountain should be higher than Blackpool Tower.
No one says trigonometry breaks down. If you had a piece of paper that was 10 billion miles long and you drew a triangle on it, trigonometry is still going to work. It's the application of trigonometry to observed physical or optical phenomena that is ruled by perspective and a whole bunch of other phenomena as you look out into the distance.
Brandon, you seem to forget that perspective is the visual angle that a viewed object subtends at the eye, and the visual angle is the same as angular size, and we calculate angular size with trigonometry.
You can't do that. That's not the same as measuring something physically. You're measuring optical phenomena. You're not measuring something physical.
Optical phenomena are any observable events that result from the interaction of light and matter, otherwise known as physical objects. Well, this seems to be the latest flat earth meme. You can't measure optical phenomena. Well, first of all, everything in this photo is a physical object that has an actual size and an actual distance from the observer. And the hypocrisy is that globers have done the exact same thing that flat earthers do when they use photographs to try to disprove the globe. They go to Google Earth to get distance and elevation data, and they do a Google search to get building heights and mountain elevations. But there is a second part of this that does need to be addressed, because there are two optical phenomena that do affect observations. The first one down here is mirages. And here are three examples of mirages that we might see. Now, inferior mirages are the most common, and they do obscure things in the distance, but they're pretty easily dealt with. If we can find a photograph of the object in question, scale it to the picture, we can determine how much of that object is being hidden by the inferior mirage. So in this upper photograph, this would be evidence of a globe. If it turned out like this photograph down below, that would not be evidence of a globe. Now, refraction is the other phenomena that can change what we see. So here are two more photographs that everyone is familiar with, and they are taken by the same individual from the same location. Now, the photo above has minimal refractive distortion. If you compare these oil rigs to close-up photographs of them, everything looks proportional. But the photograph down below, the refractive distortion is quite obvious. Now, the most obvious is the towering in this area right here. Look how that crane boom curves up. And there is also obvious looming. In the top photograph, this arrow here is aligned with this deck on the platform on the right, and there's also a little bit of a deck sticking out over here on the left platform. In the lower photograph, you can clearly see that that deck has loomed higher in relationship to this deck over here.
What breaks down is the model, not the trigonometry. That's where you're confused.
No, I'm not confused at all. Your confusion is that you think you can apply trigonometry to these long distance site observations.
Why can't we? At what distance does trigonometry break down?
You're saying on a flat earth this should, then you're applying trigonometry, and then you're saying this method doesn't work, therefore the earth isn't flat. You made up a straw man for how you think it should work, then applied it, and it didn't work. And therefore, you said you're falsifying it. This is not our model. No one is saying you should be able to do this.
Now, flat earthers are right. We do not live on a model, but we also don't live on words that we use to explain the world around us. And that's all a model is. It's an explanation. So scientific modeling is a scientific activity, the aim of which is to make a particular part or feature of the world easier to understand, define, quantify, visualize, or simulate. And down here, we can use mathematical models to quantify and graphical models to visualize the subject. So let's be honest, when you define the Earth is flat, you have defined a physical model of that Earth. the globe and flat Earth are two different physical shapes, two different models. Now we can apply math to both models. So again, the math we would use on a flat Earth is trigonometry, because elevations on a flat Earth model are based on flat mean sea level water. Therefore, on a flat Earth, the height and distance of an object forms a right triangle. Brandon agrees that trigonometry works. So why is this not a legitimate way to model the flat Earth? So is this really a straw man, or just a lack of understanding of how the flat Earth would work?
You're measuring optical phenomena. You're not measuring something physical.
Again, everything in this photo is a physical object, and we are doing the exact same thing that flat earthers have done with photographs. And especially when the globe community tries to use photographs where the visible optical distortion is minimal. Because a lot of the flat earth evidence is where the optical distortion is plainly visible. And of course, we all know that this black swan photograph has become one of the icons of flat earth truth. But they completely ignore this photograph taken by the same photographer, and BML SB69 even admitted that this is what he usually sees. And flat earthers like to spend a lot of time with their cameras very close to the water level where these refractive phenomena are most common. So I guess we could ask the question, why don't flat earthers provide measured evidence of their model? Well, my answer would be because unless there is severe refraction, it fails every time.